nanotechnology acquires the giving solutions for real world physical problems. So some of the nanofluid applications are listed as nanofluids are used as superfluids in many electronic devices like cell phones, laptops, and also used as coolants in heat transfer equipments like heat exchangers, electronic coolings, and radiators. And one of the major important application with variable wall temperature that includes, and it has a wide range of applications in marine engineering, aerodynamics, rocket sciences, etc. Next, we move on to wavelets, where since we are using numerical technique, that Haar wavelet collocation methods, for that we require the definition of wavelets. And the wavelets are the mathematical tools or functions that decomposes frequencies and we can analyze them separately. And the Haar wavelet, which was basically given by Alfred Haar, who was Hungarian mathematician in 1909, and we have an entire wavelet basis family on his name. So this is what about wavelets, and we can use wavelets to decompose the data and also removal of noise and pattern classification and some more applications. So next, we have done some literature survey for our papers. Some of them are listed as Kudanetti, Avaluddin, Joshi, Chen, SEO, Lepik, and FFE. And next, here, this is the formulation of the problem, and I have given the governing equations, which are in equation number 1, 2, 3, which are, first one is equation of continuity, equation of momentum, and equation of energy, along with the boundary conditions which are given in the equation number 4. And these equations can be solved by using similarity transformations, which are given in the equation number 6. And after applying or using the similarity transformations, we reduce the partial differential equations into system of ordinary differential equations along with the boundary conditions, which are given in the equation number 7, 8, and 9. And these equations we are solving by using the numerical technique called Haar wavelet collocation method. And since we are using different nanoparticles like copper, alumina, titanium oxides, we require some basic properties. So the thermal physical properties of basic fluid and nanoparticles are given in table number 1. So next we move on to methodology, that is numerical solution. Here we will consider the solution, Haar wavelet solution, in terms of higher order derivatives given in the problem, that is f triple dash and f double dash, and lower order derivatives are obtained by using boundary conditions, and which are given in the equation 15 to 19. And along with that, we apply Cauchy linearization technique, so that non-linearity will reduce into linearity picture. And those equations are given in the equation number 20 and 21, along with the boundary condition 22, where the coefficients are like alpha 1, alpha 2, alpha 3, and also beta 1, beta 2, and beta 3. After substituting equations 13 to 19 and discretizing equation 20 and 21, we get the system of linear algebraic equations, which are given in the equation number 23 and 24, and these equations can be solved to obtain the collocation points, which can be from collocation points we can obtain the numerical solutions while substituting into original equations. And so equation 23 and 24 can be solved by using MATLAB software. So from that we obtain Haar wavelet coefficients, so that we can approximate our solutions by using those Haar wavelet coefficients. And also here we are concentrating on physical parameters like f double dash of 0 and theta dash of 0, which are numerically determined determined by the equation number 25 and 26. So here we can obtain the numerical solutions by using Harvey-Wavelet collocation method. Next we move on to result and discussion. Here I have presented and compared our results with previous literature, and also we have got the similar values which I have shown in table number 2. For the parameters, suction injection parameter 0, magnetic field parameter that is 0, along with the moving wedge parameter that is lambda is equal to 0. And I have some representations of graphs which defines the local Nusselt number skin fictions over different parameters like magnetic field, suction injection parameter, and also for different values of solid volume fraction phi, and some of them I have shown here. So these are the graphical representation of results. And next we come, finally I conclude my presentation that from above result and discussion I can conclude that shear stress increases as heart rate pressure gradient parameter, that is beta, varies and increases. So we can see that from the difference in the table number 2 which has earlier shown. And next, as increase in the different values of phi and also different values of magnetic field m, the skin friction coefficient also increases for the suction case, and also for different values of suction and injection, that is from we can move from injection to suction. There is a difference in that skin friction coefficient and local Nusselt number, that skin friction coefficient decreases as suction increases, and also local Nusselt number decreases since injection increases. So these are the conclusions from the result and discussion, and I have some references which I have referred for my work. And finally, thank you. Thank you so much.
Pointer publisher. Pointer.
Good evening to all. Myself, Dr. Lingaraja Mangadi, Associate Professor, Sri Siddheshwar Government First Grade College, Nargund. Today is my paper entitled Geneva Wavelet Based Galecki Method for the Numerical Solution of Boundary Value Problems. Now, the abstract is boundary value problems are commonly encountered in various domains of engineering and science. including gas dynamics, nuclear physics, atomic structures, and chemical reactions. Now here you have used Gannon-Barr wavelets as a weight functions. Then you obtain the numerical results using Galerkin method and compare these methods with the existing methods. My content is, first is introduction, preliminaries of Gannon-Barr wavelets, method of solution, numerical implementation, and conclusions. Now introduction, it is vital to note that most of the differential equation arising from the modeling of physical phenomena do not always have known analytical solution. Thus, the need for the development of numerical approaches to find approximate solutions becomes essential. The Galerkin method is one of the most known methods for finding numerical solutions of differential equations and is considered the most widely used in applied mathematics. Its simplicity makes it perfect for many applications. The wavelet-Galerkin method is an improvement over the standard Galerkin methods. The advantage of wavelet-Galerkin method over finite difference or finite element methods has led to tremendous applications in science and engineering. An approach to study differential equation is the use of wavelet function basis in the place of other conventional piecewise polynomial trial functions in finite element type methods. Now these are the definition of wavelets and 2.1, and here function approximation is, now the first few Gannon-Barr wavelet basis for k equal to 1 and m equal to 3 and lambda equal to 2 are as follows. Then function approximation is given in 2.5 and truncating the above infinite series to finite series, that is in 2.6. Now method of solution, consider a second order differential equation 3.1 with boundary conditions 3.2 where alpha and beta are constants and either functions of x or fx be a continuous function. Now you have to take the residual 3.3, that is Rx, where Rx is the residual. If Rx is 0, then Yx is the exact solution for the given equation. Consider the trial solution for equation 3.1, which is given 3.4, where the C and M's are the unknown coefficients to be determined. Now we go for the error is obtained using E max is equal to maximum of y of x minus y of a. Here y of e and y of a are exact and approximate solutions respectively. Now here numerical implementation. Consider 4.1 with boundary condition 4.2. Now we have explained the implementation of the solution of equation 4.1 as explained in the section 3. Now consider the residual, that is 4.3. Now choosing weight function as Wx is x into 1 minus x, which are satisfied by the boundary conditions, that is 4.2. Then now you are assuming the trial solution as 4.4. Then equation 4. You are substituting the Gannon-Barr wavelets psi10, psi11 and psi12, that is 4.5. Differentiate equation 4.5 with respect to x and substitute the values of y and d square y by dx square in equation 4.3. We get the residual equation 4.1. Now the weight functions as the same as the basis function. Now this is 4.6, that is the Galerkin method. Now for m equal to 0, 1, 2, it is 4.7. Now here 3 equations and 3 unknowns you have obtained, that is system of algebraic equation. Using Gauss elimination method, you obtain the unknown C10, C11 and C12. Then substitute these values in equation 4.5, you obtain the numerical solution. The comparison of numerical solution and the absolute errors are presented in table 1, and the numerical solution with the exact solution of equation 4.1 is given by y of x is equal to sin x by sin 1 minus x in figure 1. These are the comparison of numerical solution. Now reference 9, which is using Bernoulli wavelet method, and this is GWGM, that is Gannon-Barr wavelet Galerkin method. You have compare with exact solution, the Gannon-Barr wavelet Galerkin method is more accurate than, that is reference 9. You observe the absolute error. Now for reference 9, absolute error is 1.4 to the 10 power, into 10 to the power minus 5, but it is 2 into 10 to the power 6. Now this is the comparison of numerical solution and exact solution of 4.1. Now this is the second equation, that is 4.8 with boundary condition 4.9. Now here, this is again comparison. And this is the graph for numerical solution and exact solution of 4.2. Now the conclusion, in this paper, we have proposed the Gann-Wallace wavelet based Galerkin method for the numerical solution of boundary value problems. From the above tables and figures, we observe that the numerical solution obtained by the proposed method are better than reference 9, that is Bernoulli wavelet, reference 10, Euler wavelet, and which are nearer to the exact solution. The absolute error from this method is very less as compared to with Bernoulli wavelet and Euler wavelet. Hence, Gann-Wallace wavelet based Galerkin method is very effective for solving boundary value problems. These are the references. Thank you.
Good evening all. Myself, Dr. Basaraj Yugar, Assistant Professor, SDM, College of Engineering and Technology, Dharwad. Today I am going to present a paper titled A Novel Wavelet Method for the Numerical Solution of Neutral Differential Equations with Proportional Delay. Already you have heard about differential equations and you have studied about differential equations and different types of differential equations and their solution. But here these differential equations are little different than the normal differential equations. That word is called as delay differential equations. Okay? The differential equation means dy by dx you are writing, dy by dt you are writing. Means the dependent variable, independent variable are varying with respect to only one variable and there is no delay in obtaining the solution. But delay differential equation means the previous factor is affecting the present differential equation. Therefore, the word term or the word delay is used. The outline of the presentations are including abstract, introduction, wavelets, Laguerre wavelet method of solution, numerical experiments, conclusion, and lastly reference. The abstract of the paper is very simple. In this paper, we have developed the well-efficient numerical technique for solving delay differential equations which are neutral in nature. The scheme is based on the Laguerre wavelets. A fundamental concepts of wavelets and Laguerre wavelets are used to convert the delay differential equations into system of equations, and by solving those system of equations we obtain the results. The results with graphs explicitly reflects the efficiency of the and accuracy of the applied methods, and it can be extended to the other methods. Introduction. The theoretical and computational advancements in delay differential equations reveals that the delay differential equations are capable of generating rich and convincible dynamics with realistic parameter values. Naturally occurring complex delay differential equations, you have carried the experiment called a tuning fork in physics. Okay, so if you taken that tuning fork away from that fork, actually again sound is hearing, means the sound that whatever is there in the past is affecting the present. So like that there are some systems in the delay differential equations that affected by the previous one, and solving such delay differential equations is not an easy task because the previous fact is affecting the present parameter. Therefore we are going for the numerical methods which are complex in nature and we can easily analyze by using the delay differential equations. So here we are going to consider this general delay differential equation, and this is the different wavelet definition, where it is having two parameters. One is dilation parameter and the other one is translation parameter B. This is psi of AB of t is equal to given by equation number 2. And here we are defining the Laguerre wavelets. Laguerre wavelets are usually defined by using the Laguerre polynomials, where you have studied Bessel functions, other functions. Here, by using Legare polynomials, we are defining the Legare wavelets, and here we are having psi of 1, 1 of t, psi 1, 1, 1 of 2, 1 of 3, and so on. They are the basic parameters of the Legare wavelets. And at the beginning, now we are going for the method. Here we are going to approximate the solution y of t equal to summation given by k psi of n of t, where k is the constant and psi nm of t is the Legare wavelet. And by taking into that consideration, we are substituting these approximations into the given differential equation, that is given by equation number 10. And here we are using the initial conditions, and that initial conditions are only 1 or 2, y of 0 equal to 1, y dash of 0 equal to 1, like that. To develop few more differential equations or the number of systems, we are using this Ti, which is given by equation number 1. And then you know how to solve the system of delay differential equation. Means we are using the form Ax equal to B, where A is the coefficient matrix, B is the unknown matrix, and X equal to RHS terms. So if RHS is 0, that you are calling it as homogeneous differential equation. If RHS is not equal to 0, then you are calling it as non-homogeneous differential equation, where it is having the solution in the form Cf plus Pi. But here we are solving it by Newton's iterative method. Okay, that is called by that is by rule Ax equal to B. Then you are obtaining the solution for all the terms. Then by substituting in the actual equation, we are getting the original solution. For example, we are taking equation number 12 with the initial condition y of 0 equal to 1, and the order of the equation is 1. Okay, and here first step we are approximating as given in equation number 13, and secondly we are substituting this approximation in the given differential equation given by equation number 14, and we are having only one initial value, that is y of 0 equal to 1, and by substituting that we are obtaining the equation 15. But how many parameters are there? We are taking 5 parameters, k1, k11 of m, k12, k13 and k14. Remaining all they are constructing by using that collocation point, and remaining equation number 16, 17, 18 and 19 are collocating by using those terms. And how many equations we are having here now? 5 equations. So again, by using Ax equal to B form, we are solving the equation and we are obtaining the solution for k1 of 0, k11, k12, k13, k14. They are the coefficients, constants. By substituting these constants into the actual approximation, we are getting the approximate solution. And that approximate solution we are comparing with the exact solution. Then we will understand whether we are getting accurate solution or not accurate solution. Okay. So the exact solution of this equation is y of t equal to e raised to minus t, and we obtain the solution, and this is the exact solution for t equal to 1 by 16 at 1.93, and for our method is having also same solution. And this also we have shown it by the graph. If you observe the graph, you will understand the exact solution point and our numerical method by using Legare-Wavelet method find both are coincidence. Therefore, our calculated solutions are lying near to the exact solution. Hence, our method is giving more accurate solution. Means the solution which is lying near to the exact solution. Similarly, we have solved one more equation given by equation number 21, and the exact solution of this equation is y of t equal to t square plus 1. And here we are having two initial conditions, y of 0 equal to 1, y dash of 0 equal to 0. Again, by applying same method we have solved, and here also we are obtaining the almost same answer, which is just like a exact solution. And this is the graph of the second problem. Again, you can look into the graph. Here the points of the exact solution and present method are having same. Then this is the one more example you have solved, y double dash. This is second order differential equation, and the exact solution of this equation is t square. By using same method, we have solved it, and again the present method, which is at the last column, is coincident, is having same solution given by the different parameters. And this is the graph. And lastly, we have one more non-linear neutral differential equation, which is non-linear in nature. The exact solution of this equation is again t square, and again we have solved by using same method, Legare-Wavelet method. The exact solution and the Legare-Wavelet method solutions are almost one and the same. And this is the graph for this method. By looking into all these tables and graphs, we can easily conclude that we can easily solve the neutral delay differential equations by applying the Legare-Wavelet method, which is very easy in nature, and that we can extend it for other models also, mathematical models which are linear and non-linear in nature. And these are the references we have referred to construct this paper. Any doubts, any questions, you can ask freely. You heard at least about wavelets. Psi of AB of t equal to. If there are no questions, then we are at the end of this session. Okay, thank you.